Okay, I think we can start with the intro. Hi, everyone. Good morning, good afternoon. I hope you can hear me. If you can't, please post something in the chat. Great. My name is Todd Evans. I'm from the Texas Advanced Computing Center at UT Austin. I'm a research scientist there and collaborate with Ricardo and other colleagues from Portugal. I'm here to introduce you again to this initiative, which is a joint webinar series between the BigHPC project and the UT Austin Portugal Program. I wish to thank you for participating in this session. In this webinar, we'll welcome Ricardo Macedo from INESC, who will talk about user-level defined storage data planes. So Ricardo is a researcher at HASLab INESC. He's a fourth-year PhD student at University of Minho. His research interests include local and distributed storage systems with a particular focus in software-defined storage, programmable and distributed storage, and kernel user space storage technologies. Currently, he's working on a software-defined storage data plane framework for enforcing end-to-end performance policies in complex storage infrastructures. As I said before, my name is Todd Evans, and I'll be the moderator of this session. I'd like to let you know that you can and should interact during the presentation. To do so, you can use the chat to share your questions. During the presentation, there won't be any discussion moments, however. It just simplifies things in this virtual format. But at the end of the webinar, we'll provide a number of minutes to discuss all the questions that you all bring up and interact directly with you. I'll be monitoring the chat activity and recording the questions as they arrive. And finally, please keep your microphone muted during the presentation to prevent background noises. And we will start maybe in a minute or two, give people a little bit more time to show up. And the presentation should be about 40 to 45 minutes, after which, like I said, we'll have a number of minutes to discuss any questions that are raised. So with that, I'd kindly ask Ricardo to share his screen. And in order to kick things off, Ricardo, the screen is yours.
Okay, so thank you, Todd, for the very welcoming introduction. So I'm Ricardo, and I'm here to discuss a bit of the research that we have been conducting in these few years at INESC, and it will be more on the side of user-level software-defined storage data. So in this talk, I will not focus so much on the general knowledge about cloud and HPC infrastructures. Okay, you can check the previous webinars on the first series. Okay, and in this talk we will discuss a little bit more on the details of the storage part and so forth. So this talk will be mostly made around three parts. Okay, a first part regarding the contextualization and give a bit of a background on the problems that we are trying to address. The second part on how we are addressing these actually addressing these problems. Okay, and the final part where we build some solutions to actually overcome existing problems in production. So first of all, data-centric systems such as databases, key-value stores, file systems, machine learning engines, and so forth, have become an integral part of modern IO stacks. And in these IO stacks, but I mean cloud and HPC infrastructures, okay, that are composed by several nodes and several layers throughout the IO stack. And good performance for these systems often requires several and pretty complex storage optimizations, okay? Like schedulers, caches, tiering, replication, you name it. And for these optimizations, we believe that they are implemented in a suboptimal manner. And let me just show you a simple example of this challenge that we are having, okay? So let's consider a simple I/O stack made of an application, a key value store. So a key value store is basically a storage system that stores and retrieves data in a key value format, okay? And these files will be then stored at a traditional file system, at the kernel space. So the first challenge is that these optimizations, we don't actually think most of the times, but these optimizations are single purpose because they are implemented inside the layer that we are targeting, okay? So these optimizations such as I/O schedulers, caches, steering are implemented within applications, in this case, the key value store. And this raises some problems. First, it requires deep understanding of the system's internal operation module. Second, it requires a profound system refactoring, okay? And we are talking about code bases that can have a few thousands of lines of code to millions of lines of code, okay? And this is pretty complex. The third part is that when we do this, we are limiting the portability across systems. So if we implement these optimizations over a specific value store, it is pretty difficult to implement over others, okay? So let's consider a simple example where we have, let's consider Silk, okay? Silk proposed an I/O scheduler to reduce the 10 latency spikes in RocksDB. And it does this by controlling the interference between foreground and background tasks. And regardless of the amazing performance results they can achieve, they require changing several core modules of RocksDB. So such as background operation handlers, internal queuing logic, thread pools, and so forth. So one way that we can actually address this problem is by decoupling this optimization, okay? And by this, I mean that these optimizations can be disaggregated from internal system logic and moved to a dedicated I/O layer. And this will then become generally applicable and portable across different storage scenarios, okay? But this raises another challenge, and this is mostly the cause on optimizations are most of the times not decoupled. So when we do this, we probably lose the granularity and the internal application knowledge that we have when designing that type of optimization. Okay, so by doing this, I/O layers, since I/O layers communicate through pretty rigid interfaces such as POSIX, we may be discarding information that could be used to classify and differentiate requests at different levels. Okay, so consider again our key value store example. Key value stores basically submit operations to the file system using foreground flows, compactions, and flush. Okay, but from the perspective of the file system, it only sees POSIX operations, right? So reads, writes, open, closes, and so forth. So it doesn't really know where that operation is coming from. So if it is from a foreground operation, a compaction, or a flush. And if you want to design optimization specific for those type of requests, it is pretty difficult to achieve, okay? So another thing that we can probably do is by propagating information, okay? So application level information, so that is only known to the application itself, in this case, the key value store, must be propagated throughout the I/O layers. So this way, the decoupled optimizations can now provide the same level of I/O control and performance as system-specific ones. Okay. Another problem that we watch is that, okay, so by disaggregating layers, we can probably do this implement them on the file system, right? Or the block device, because they are more generally applicable. But this is pretty difficult, okay? Because propagating the context to kernel requires breaking user to kernel and kernel internal APIs that are legacy. So user to kernel, we have POSIX, kernel internal, we have communication between the file system block device interfaces, the file system internal modules, and so forth. And other problem is that the kernel level development is pretty difficult compared to the user level one, okay? Because it is way more restricted and much more error-prone, and can introduce bugs that we are not aware of. And the other problem is that the optimizations, when we consider modern storage stacks that are made of NVMEs, persistent memory devices, that are carried with SPDK and PMDK toolkits that allows us to implement storage services on user space that completely bypass the file system, block device, and page cache levels, these optimizations would now be ineffective, okay? So one way to address this is that the dedicated layer layer should then actuate at the user level. So optimization should be implemented at user level, and this also promotes the portability across different systems and layers, okay? And not only that, but also eases the information propagation throughout the different IO layers, okay? Finally, another aspect that we watch is that this, let's consider now that we have, again, our application key value store, but we have separate instances. So that can either be running locally or running on a distributed setting. But in most cases, they are sharing a file system. So either local, such as XT4 or XFS, or distributed, such as Lustre, GPFS, BGFS, you name it. So in this case, since each optimization runs locally or in its own scope, they are not aware of the other system, so they are oblivious. And this results due to a lack of coordination between all of these optimizations. And this may lead optimizations to conflict with each other and lead to IO contention and performance variation, okay? So one of the things that we can probably do is to, well, let's introduce global visibility, okay, and achieve global IO control. So in this case, optimization should be aware of the surrounding system stack and operating coordination. So this ensures holistic control of IO workflows and holistic access to the shared storage resource. So this ends part one, okay, of the talk where I explained the problems. So now that we know this, let's consider how can we actually design a storage data plane framework that fits all of these requirements, okay? So for this, we have designed PIO. PIO stands for Programmable and Adaptable IO, and is basically a user-level framework that allows system designers building portable and generally applicable storage optimization. So PIO adopts ideas from the software-defined storage community. So software-defined storage, João Paulo already explained this on a previous webinar, but basically allows us to, is a separate paradigm for developing storage systems that we separate the data from the control. So where the actual IO will flow and how we control things, okay, and how things should be orchestrated. So in this part, we have the data plane and the control plane. And for our scenario, IO optimizations, so schedulers, rate limiters, compression schemes, encryption schemes, should be implemented outside of application. And they will act as data plane stages. Then stages will be controlled through a control plane that has global visibility over the storage resources and allows coordinated access to everything, okay? Also, PIO leverage from the previous things that I was mentioning around propagating the application level information through context propagation. So context propagation is a pretty known technique on distributed systems monitoring that allows you to propagate a little bit of information that is only known to the application itself throughout the rest of the IO stack, okay? And porting IO layers to use PIO requires none to minor code changes, as you will see in a bit. This work PIO was published recently and presented on Usenix Fest, and we are still working on it and continue to improve it. So let's see a bit how PIO works and how its design affects all of the challenges that I've been discussing. So first, PIO is provided as a user-level library that allows system designers to build custom-made data plane stations. So in this case, each data plane can sit within or between IO layers. So within an application or between an application and another layer, so let's say the file system, and is provided as a dedicated I/O layer that has its own logic. PIO activates at the user level and communicates throughout the entire execution with a control plane that has the global visibility. So PIO provides 4 main modules that allows us to communicate and achieve different things. So the first part, it provides a stage interface that provides the access point for applications to actually communicate with PIO, to enforce the requests and so forth. And this will basically forward the application requests to the PIO stage. Then it provides a differentiation module. This allows us to classify and differentiate requests at different levels. So basically, let's say that I want to receive a write request and treat it in a specific way, and then receive a read request and treat it in another way. So this allows us to classify the requests, differentiate them, and actually generate some metadata that will allow us to enforce the specific policies that we want over those requests. The differentiation model also allows the context propagation that I was talking a bit, and it allows different levels of differentiation. So it allows differentiated requests by the operation type, so reads or write requests, the operation context, which is the origin of that given request. So if it's coming for a foreground flow or a background flow or a flush, let's say that, okay. Its operation size, workflow identifier, the application that it was submitted, and so forth, okay. Then we have an enforcement module. The enforcement module allows us to apply the actual I/O logic, okay, over the requests. So this logic is the actual I/O mechanism and can be implemented as token buckets for achieving rate limiting, encryption schemes to cipher private information, compression schemes to actually reduce the data, implement caches, and more, okay? And for this part, we have 2 different abstractions, channels and enforcement objects. Channels are basically to where the request will flow, okay? And then each channel has several enforcement objects that can apply the different I/O mechanisms over the requests. And this can be a single enforcement object or multiple, okay? So in the same channel, you can apply different things, rate limit, compression, caching, okay. So the final step is that PIO exposes a control interface to enable the control plane to continuously orchestrate the stage. And this is important because we can have multiple data plane stages across our infrastructure, and we want to continually monitor its state and fine-tune it. So to better understand all of these concepts work together, let's consider again our previous stack. So the application, the key value store, in this case, RocksDB, and the file system. And now we have a PIO data plane stage that sits within RocksDB before the requests are submitted to the file system. And in this case, let's consider that we want to actually enforce the following policy. Limit the rate of RocksDB flush operations to X megabytes per second, okay? So the first part is that, as I was saying on challenge 2, we don't really know through where the requests are coming from on the POSIX, okay? So if it is a foreground, a compaction, or a flush. So the first step is to identify the origin of these requests. And to do that, we first instrument the critical path of RocksDB, where these operations are created, and we tag the request using context propagation to say that this given request is a foreground, this given request is a compaction or a flush, okay? Next, the request, before being submitted to the file system, is first submitted to the stage interface, so to PIO. In this case, for each request, PIO will generate a context object. This object is basically a metadata object that classifies and characterizes a given request. And basically, it will accompany the request by identifying the workflow ID, the type of the operation, the context of that operation, the size, and more, okay? So after that, both the request and the constants are then submitted to the PyData plane stage, and it first needs to be differentiated. So in the differentiation phase, we have basically the type of request that each channel should handle. Okay, so let's say that we have two channels, channel 1 and 2, and channel 1 should handle requests that are coming from flushes, and channel 2 should handle requests that are coming from foregrounds and compaction flows. Okay, so the request is then is differentiated and submitted to the respective channel. In the channel, it will be first submitted to a submission queue and will then be dequeued by an enforcement object. Okay, so in the case of channel 1, where we only treat flush operations, and to comply with the policy, we want to rate limit it, we provide a dynamic rate limiter enforcement object. So this dynamic rate limiter is basically a token bucket that will only submit requests at a given rate. Okay, so after the dynamic rate limiter enforces the request is then returned to the original base. On channel 2, it supports a NOP enforcement object that will basically act as a pass-through. So it will implement anything over the foreground or compaction flows. So the requests are then returned to the original data path and are submitted to the file system. At this point, the requests are already enforced, and the optimization that we wanted to apply is already in course. Okay. Throughout the entire execution, the PyData plane stage continuously interacts with the control plane through a predefined control API. So first, the control plane will define how each data plane stage will be actually organized, okay, by housekeeping rules. This will basically create the channels, associate enforcement objects, and so forth. Then it will define how requests should be differentiated through differentiation rules. It will continually collect the statistics from each data plane stage, okay, to ensure that the policy is actually being enforced correctly by collecting, for example, the rates or the amount of operations that are arriving at the data plane stage. And based on that information, if the policy is being met, great. If the policy is not being met, it will basically fine-tune it and submit an enforcement rule to adjust the dynamic rate limiter. Okay, and this control plane implements the actual control algorithms. Okay, so in this case, if we wanted to set the rate at a given megabytes per second, the control plane will only implement a feedback loop that continuously collects statistics and check if everything, if the flush flows will then be submitted at that megabytes per second. Okay. So this concludes part 2, and on part 3, now that we know how PyO is implemented and how it resolves the previous challenges, let's consider which type of data planes we can implement and which type of problems we can address. Okay. So in the first problem, we consider how can we address and resolve the problem of tail latency control in log structure merge tree-based key-value store. So RocksDB is a key-value store of the type LSM. So LSM is a log structure merge tree that defines the internal organization of data that is basal compound on different levels. Okay, so level 0, level 1, level 2, so forth. And on this type of key-value stores, it is pretty well known that there is high interference between foreground and background tasks, and this generates high latency spikes to the client. And these latency spikes occur because L0 to L1 compactions and flushes are either slow or are on hold. Okay. So to address this problem, Silk proposed a very interesting solution that provides an I/O scheduler that is able to allocate bandwidth for the internal operations when the client load is low. So it basically adjust the rate of internal operations when the client requests are not as frequent as previously, not as intensive on that specific period. The second point is to prioritize flushes and low-level compaction. And the third point is to preempt high-level compactions with low-level ones. So by preempting, I mean that it basically stops the execution of high-level compactions to do more high-priority compactions, so the low-level one. Okay. And besides the performance that Silk can achieve on this case, it requires changing several core modules made of thousands of lines of code. So RocksDB currently has over 500,000 lines of code, and tracking down all of the files and all of the classes and modules that we need to change is pretty difficult. Okay, so we come up with a different approach. So on Pio, we implemented a stage that provides the building blocks, so the I/O mechanisms for prioritizing and rate limiting all the background flows. Okay, and integrating the data plane stage in in RocksDB only requires changing and adding 85 lines of code, of which half of them were to achieve the actual context propagation part that I was saying earlier. And since Pio follows the software-defined storage approach, the design is made in a two-phase. So the data plane stage will provide the mechanisms, and on the control plane, we implemented a Silk-alike I/O scheduler. Okay, so the algorithm part. In this algorithm, we are able to actually allocate the bandwidth for internal operations. We are actually able to prioritize flushes over and low-level compactions, but we are not able to preempt high-level compactions with low-level ones. And why is that? Because we don't want to be that intrusive, because it requires changing several core modules, okay? But the thing is that we will prove on the evaluation part, is that by propagating application level information to the data plane stage, so information that is only known to the application itself, the Pio data plane can enable similar control and I/O performance as a system-specific optimization. In this case, the Silk's I/O schedule. So for the actual evaluation, you can see the paper for much more results and interesting insights about the framework. But in this case, I will only focus on a specific workload. So in this case, we evaluated the RocksDB, Silk, and Pio use cases using only observing the metrics of throughput and 99th percentile latency. So in this case, we had a benchmark submitting 8 client requests in a mixture-based workload, so 50% reads and 50% writes. We had 8 client threads, and each of the key value stores were configured with 8 background threads. And the workload was bursty, made of peaks and valleys. So as you can see by the plots, the workload follow a first loading phase of 300 seconds that submits operations at 5,000 operations per second, followed by peaks and valleys of 100 seconds and 10 seconds. So peaks would submit operations at 20,000 operations per second, and valleys would submit operations at 5,000 operations per second. So as you can see, on RocksDB, and due to the problem that I was previously explaining, on throughput side, it shows high variability due to constant flushes and compaction. And on a 99th percentile latency side, it provides high tail latency with peaks that can range between 3 and 15 milliseconds. And there was sometimes that the latency achieves 25 and 30 milliseconds mark. So when we go to Silk, we are able to see that the I/O schedule is pretty effective. Okay, so when you look to the right, the 99th percentile latency, it is pretty low and sustained across the entire execution, with most of the times never exceeded the 5 milliseconds mark. But on the throughput side, it suffers some periodic throughput drops due to accumulated backlog that was originated from the previous set. And when we go to PIO, because PIO is based on the same IO scheduler as Silk, it provides a similar performance curve regarding latency and throughput. So on the latency side, as you can see, most of the times it does not exceed the 5 milliseconds mark, such as Silk. And on the throughput side, it basically suffers from similar throughput drops due to accumulated backlog as well. The interesting thing is that both PIO and Silk observe a 4 times decrease in absolute time latency when compared to RockCV. And not only that, but also PIO is able to do this in a decoupled manner, so without changing the core models of RockCV. Okay. Another use case that we worked on, and more connected to the HPC part, is how can we achieve per application bandwidth control in a shared storage setting? So for this use case, we discussed a bit with the AIST folks, okay, at the AIST Research Center, that they have the ABCI supercomputer, where jobs can be co-located in the same compute node. And each job runs with dedicated CPU cores, the dedicated memory, GPU, and storage quota. However, the problem is that the local disk bandwidth is still shared. And this will lead to all of these jobs that are co-located will compete for the IO and generate IO interference and performance variation. So one of the things that we could probably do is to use BLK-IO. So Cgroups block IO controller allows static rate limiting read and write operations. The problem is that on the ABCI setting, to change, since this rate is static, to change it, we need to stop the execution of the job, adjust the rate, and restart the job again. Okay, and this would be pretty expensive in terms of performance. So because of this, throughout the entire execution, the jobs cannot leverage from leftover bandwidth, and this will lead to suboptimal performance, okay, and waste of system resource. So one of the things that the approach that we come up with PIO is that we implement the data plane stage that provides the IO mechanisms to dynamically rate limit workflows of each instance. Okay, so each of the jobs that will be collocated in the compute node. So in this case, we considered a TensorFlow job. So TensorFlow is a machine learning, deep learning, like a framework that allows training different models. Okay, and it can, on the training phase, it is pretty IO intensive. Okay, in this part, we integrated PIO in TensorFlow without changing any lines of code. And how do we achieve this? By using LD preload. LD preload is an operating system primitive that allows to basically replace instructions and function calls from dynamically loaded libraries at runtime. So basically what we are doing is that we are able to replace libc's read and write function calls for PIO's read and write system calls. Okay, so basically the request, instead of going directly to the file system, it will first be submitted to PIO, and then it will be submitted to the file system. Okay. On the control plane, we provide a proportional sharing algorithm that follows a max-min fair share kind of design that allows to ensure per application QoS guarantees. Okay. So in this scenario, we evaluate 3 different phases. So the baseline, that is the common usage of jobs on the ABCI supercomputer, BLK-IO, and PIO. And for this, we have 4 working instances, each running a TensorFlow job that has access to dedicated compute and memory resources, but the disk, the local disk is shared. Okay. And to demonstrate an interesting scenario where we actually provide QoS, we define 4 different policies. So instance 1 only has access to 150 megabytes per second, instance 2, 200 megabytes, instance 3, 300 megabytes, and instance 4, 350 megabytes per second. Okay. So this, all of the instances sum up would come to 1 gigabyte per second of bandwidth. So as you can see, throughout the initial execution of the first instance of TensorFlow, each phase will basically correspond to a new instance coming in or leaving. Okay, so 1, 2, 3, 4, 5, 6, 7 represents the separate events of an instance joining or leaving the compute node. So as you can see, at the first part of the execution, ABCI is able to ensure these guarantees, okay? Because they are basically sharing fairly the resources. But when the fourth instance come in, the instance 3 and 4 cannot meet their bandwidth guarantees. And why is that? Because instance 1 and 2 are over-provisioned and consuming more bandwidth than the one that is defined on their policies. So instance 1 consumes more 100 megabytes per second, and instance 2 consumes more 59 megabytes per second. And one way to address this is by using BLK-IO. So in BLK-IO, as you can see, throughout the entire execution, all instances are able to achieve their bandwidth limits. But one of the problems is that either when, because we have leftover bandwidth, instance cannot be dynamically provisioned with available disk bandwidth. So the rate is static and does not change throughout the entire execution. And this basically will lead to loss of the consumption of the resources and optimal usage of the resources, and will lead to longer periods of execution. So when we compare the baseline approach, even though we were faulty in terms of not complying with the policies, the execution finished around 53 minutes, sorry. And on BLK-IO, the instance 1 was running throughout 95 minutes, okay? So in our approach, PIO basically comes up with both opposed worlds, okay? So PIO ensures that policies are met at all times as BLK-IO, but whenever leftover bandwidth is available, PIO shares it across all active instances as the baseline part, okay? So in this case, by doing this, we are not breaking any of the policies, and you are actually able to approximate the entire execution to the baseline one, as you can see from the result. So let's now talk a little bit of other works that we are doing on storage data planes, but now for deep learning scenarios. Okay, so these solutions were not actually implemented using PIO, but could be. Okay, but they are basically targeted for deep learning settings. So first, we have been doing some work regarding storage tiering. So we implemented Monarch, that is a framework agnostic storage middleware that allows to actually use local storage tiers of supercomputers to accelerate the deep learning training. So most of the times the data set is only stored at a shared storage premise, so Lustre, and users are not aware of the local storage tiers. So when they run their training, it will lead to a lot of more training time than they want. So in Monarch, we basically perform a transparent storage tiering mechanism that allows to accelerate the deep learning training by up to 28% and 37% in TensorFlow and PyTorch respectively, okay? Depending on the IO mode. And this is not only that, but also Monarch is pretty good by decreasing the operations submitted to the parallel file system. At most, we can achieve results at most of 56% reduction, okay? And this is pretty interesting because there are a lot of operations on deep learning that can generate some trouble to the parallel file system, more specifically on the metadata part. So opens, closes, get HTTRs, and so forth. The other solution was by implementing a parallel data prefetching. So this is also a framework agnostic storage middleware that allows prefetching training data samples before the actual deep learning framework requests. So By doing this, we can significantly outperform the baseline PyTorch and TensorFlow configurations. We have achieved the results that surpass by 50% at most. And also, when we compare to carefully engineered IO optimizations implemented on TensorFlow, we provide similar performance as those. So this is interesting because we are actually implementing these optimizations outside of the box, okay? So outside of TensorFlow, outside of PyTorch, and we are able to come up with similar results. So, and these solutions, note this, they are portable across other settings. Both of these systems were recently published on CC Grid and the RexIO workshop. And of course, check those papers to see more information of the details and the evaluations that we have conducted. So, as a summary and some takeaways, we have been working on how can you actually implement in a more intelligent manner storage optimizations. And for this, we proposed PIO, that is a user-level framework that allows system designers to build custom-made storage data plane stages. And PIO combines ideas from the soft-verified storage community and the context propagation side of things. So PIO allows decoupling system-specific optimizations to dedicated IO layers, and we show that by using user-level data planes and propagating the exact information that we need from inside the application, we are able to enable similar control and IO performance as system-specific optimizations and carefully engineered systems. Okay, and what else can we do? Well, PIO can be applied over a lot of different storage scenarios. So we can actually implement more IO mechanisms, so encryption schemes, compression schemes, caches, programmable caches, and so forth. And we can target a lot of different scenarios. So in this scenario, we only talked about the local storage settings, but it can be applied over distributed settings. So let's say that we want to enforce QoS policies over a complete infrastructure. We can achieve those by having different data plane stages at compute nodes by controlling the rate of both data operations and metadata operations. We can put different data plane stages in a vertical way, targeting different layers of the IO stack and more. Okay, and this can be applied over cloud, application specific, or HPC infrastructures. So with this, I conclude my presentation. So I'm available for some questions now. Thank you for listening. And if you want to contact me about some further collaboration, more information about all of these systems, you can check out, contact me through my email, and check out all of these projects in our GitHub's project space, so the HASLab, and also our website, the HASLab, GitHub.io. Okay, and I think that's it. Thank you, everyone.
Yeah, that was great. Thank you. If anyone has any questions they want to bring up, please try unmuting and you can ask Ricardo directly. And if you can't, feel free to just ask the questions in the chat and I can relay them to him.
Okay, I have a question. Ricardo, can you hear me?
Yeah.
Okay, it's your response. So this looks great. Of course, my interest is a little broader. So you talked about multiple applications basically on a single node. So have you thought about expanding this to multiple nodes where, say, I have a job and a job I need, so I know the node list and it runs completely in user space. So I have SSH access to all the nodes. So I can set global limits and maybe a sub queue per node to set an individual limit per node for bandwidth.
Yeah, that's a great question. And currently, we at INESC and also the tech folks, we are working on that. Basically, we can at each point of the job, so at each compute node where the job will be conducted, we can put a PIO data plane stage, and then each data plane stage will target the IO operations of that specific node, and how can we achieve the holistic approach? So the control plane will continuously monitor the information around all of these compute nodes and continuously arrange the rates at each job will be submitted to the parallel file system.
Okay.
Does that address their question?
Yeah, I mean, I find it extremely valuable if, as a user or an administrator for a job, I can set a global limit for the job, and let's say an individual limit per node, and maybe a special higher limit for the master node, because it's probably going to be doing more I/O. And I can set this in such a way that I'm limiting my job so they won't knock over our file systems.
Exactly. And not only on the data part of things, but also on the metadata part. Regarding open, closes, get HTTRs, and so forth. Currently, we have a preliminary solution that are able to actually control all of these things and provide some POS control over both local and distributed jobs.
Great. So we're definitely going to be testing this on our system.
Okay. Great. Awesome.
I'm saying that to Stephen and Amit who are on the call. Thank you.
Yeah, thanks, John. Yeah, just a follow up to that. What systems have you all tested this on at this point? Anything other than ACBIs, or are there like OS dependencies to this framework?
Yeah. Currently, we only tested applications directly communicated with the file system. So, but it doesn't, from our experience, it doesn't have any major operating system dependency, regardless of the LD preload one. So the LD preload is basically used for do the thing transparently without changing the application side. And we currently tested with RoxyBit. That was a pretty complex use case because we had a lot of different workflows. And we also tested with TensorFlow. TensorFlow is interesting because it's a single process with under a multi-threaded scenario, and PyTorch that follows a different approach. There is multi-process, and this will generate different data plane stages for each of the process. And we need to come up with a coordination solution to actually control all of those stages that are basically over a single application. And but I think they can be applied over different layers. If that answers your question.
Yeah.
Okay, so I have another question. So the way this works with LD library, the preload, you're just wrapping all the POSIX commands. So open, close, write, read.
Yeah.
Okay.
Exactly. Yeah. And so before the operations are submitted through libsys read or write operation, it will be first submitted to the data plane stage, which will then enforce the objective and then submit the operation again to the actual file system using the original libc pointer.
I guess another question would be, have you ever tested this on top of a Lustre file system?
Sorry?
Have you ever tested this on top of a Lustre file system?
Yeah, we are currently testing this on the top of a Lustre file system. Yeah.
Okay. Have you ever tested it with an MPIO code on just a single node with multiple tasks?
Yes, and it currently is working pretty well. Yeah. I'm not sure how it will work when we use another application that has a dependency on LD preload, though. If that application has a dependency on the LD preload, I think the operating system only handles one of those. I'm not sure about that.
Yeah, there's some ordering things you have to be careful of.
Yeah.
You know, on TACC systems, usually, if you're doing something, you need to unload Exalt or whatever. So our LD preload doesn't get in the way of your LD preload. Also, I'm asking about MPIO because MPIO and Lustre, right? MPIO sets up things in a specific way to work with Lustre. And it just, don't want the two techniques to optimize I/O to sort of get in the way of each other.
Yeah.
The MPIO
Yeah.
will try to write per strike, one writer per strike. But
yeah, I think that this is more of a iterative process, right? Because the first couple of applications that we are targeting is that those such like a distributed TensorFlow process or job in this case, so that directly communicates with a lesser file system. So in this case, we want to put different data plane stages over those compute nodes and adjust the rate that you want. When we go for use case that, as you were mentioning, using MPIO and so forth, well, let's see how it goes, because we are basically conflicting optimization one another, and this can be troublesome and not introduce, not actually be counterintuitive, right?
right. No, I like this a lot. If you get it working, I want to make it part of it.
Awesome. Let's work on that.
Just put the controls right there.
Let's see, we have a question from Amit. How frequently are you applying these optimizations when you're running an application? Or yeah, I guess how frequently is there sort of feedback between this service? How frequently is it tweaking things? Does that make sense?
Yeah.
Or and is that related to any kind of overhead?
That's a great question. Yeah, that depends a lot on the workload, because if it is a sustained workload, probably the data plane will need just a few rounds on the beginning, and once the workload stabilizes, the rate will be pretty much static. But whenever the workload changes, either because there was a burst on the I/O operations, or because there is leftover bandwidth, it basically needs to readjust the token buckets to ensure that it now runs in a more optimal manner. But this doesn't introduce too much overhead, okay? Because these are on the control plane part. The control plane, though, has its own challenges regarding scalability and reliability, but on the control flow of things, it doesn't introduce a lot of overhead.
Yeah, so with that in mind, is this something that maybe you envision sort of being by default enforced, like at centers, or something that could just kind of always be enforced to, say, protect the file systems, or you know, provide basic QoS?
Yeah, that's also a great question, and that basically depends a lot on the system administrator. I think the role would be the file system is first, the QoS policies of the users are in the second place, because if the users specify some crazy policies, it will most certainly lead to breaking the lesser file system. Okay, so basically, administrators need to ensure that the policies are okay. And then if there are room for actually provide the policies that the user specified, so let's then use them, okay? But yeah, that depends a lot on the infrastructure, because in different supercomputers or different research facilities orchestrate the resources in a different way. So let's see.
Do we have any last minute questions before we wrap up?
I have a last minute question. So
Awesome.
my question is, can you run some applications with higher optimizations compared to others? We know like some applications may demand more I/O compared to other scientific applications.
So basically, if we can set different policies for different applications?
Right.
Yeah, definitely. Yeah, that is feasible.
Thank you.
Maybe one last question. How are these policies set? Is it like a configuration file somewhere, or environmental variables that you set, or? Yeah,
currently these policies are set from the control plane side. Currently, because this is more research prototype, we are setting them either through a configuration file or directly on the algorithm itself. But we envision that these policies can be basically provided as a predefined set of rules. Okay, so come up with a set of language that can express enough all of these rules and policies, and then be submitted through either a job or either through Bash, something like that. Okay, so the control plane basically ingests those rules and analyzes and generates if the policy to implement is feasible or not.
Great. Okay. Let's see here. I'm going to, unless we have any very last minute questions, I'm going to wrap things up. Thanks, Ricardo. That was a really great presentation.
Thank you. My pleasure.
Yeah, thank you everyone here for your participation and your questions. I'm gonna close things down, but please stay tuned and join us for the next webinar. The subject will be building high-performance storage systems for persistent memory, and will take place on July 14th, 2022 with Rohan Kadakoti from UT Austin. So thank you for joining us, everyone, and have a great day.